Today we're going to learn lesson 4, Trigonometric Identities Part 3. So first of all, let's have a look at today's learning goals. After today's lesson, you will be able to understand and prove compound angle formulas and use compound angle formulas to solve problems, and then apply common trigonometric identities to solve problems using all the trigonometric identities we have learned so far. Okay, so today the new stuff is compound angle formula. So let's have a look at what is a compound angle formula. Okay, first of all, we're going to prove this is actually a trigonometric identity. You can write this down on your notebook first, and then let's have a look at how we can prove this. This is cosine. The sum of alpha and beta is actually cosine alpha cosine beta minus sine alpha sine beta. Okay, please write this down on your notebook. This is called compound angle formula. Okay, now let's have a look at how we can prove this is actually a trigonometric identity. Suppose there is an arbitrary angle alpha here, which has the terminal side in blue, and the term there is a arbitrary angle minus beta who has a terminal side in red, and then we know that alpha plus beta probably lies here, right? Okay, so this is alpha, this is minus beta, and this is alpha plus beta. And we also know that this angle here equals the angle here, right? Because this is minus beta, and this is alpha plus beta, so that means this angle here must equal this angle, right? Okay, so then we draw a unit circle. Unit circle has a radius of 1 unit, right? And the intersection point with the terminal side alpha minus beta and alpha plus beta are A, B, and A prime respectively. And we also denote this point here as B prime, right? And then we connect A prime, B prime, and AB. And so as you can see here, there are two triangles. Triangle OAB, which is, okay, let me use another color. Triangle OAB is here, right? And there is another angle, which is triangle OA prime B prime, right? And also we know the coordinates of point A, which is cosine alpha sine alpha, because A is on the terminal side of alpha. So according to the definition of trigonometric ratios, we know that the coordinates of A is actually cosine alpha sine alpha. And the coordinates for A prime is cosine alpha plus beta and sine alpha plus beta, right? Because A prime is in the terminal side of alpha plus beta. And the coordinates of point B is cosine beta minus sine beta, because by definition, the coordinates of B should be cosine minus beta and sine minus beta, right? Cosine minus beta is just cosine beta, and sine minus beta is minus sine beta. So the coordinates of B is cosine beta and minus sine beta. And of course, the coordinates of B prime is 1, 0, right? Because it's on the x-axis, okay? And then we know that because OA prime equals OA, and the angle A prime O B prime equals AOB, and also OB prime equals OB, right? So we know that the triangle OAB is congruent to triangle OA prime B prime, right? So if these two triangles are congruent, we have the length of AB equals the length of A prime B prime, right? And the length of AB is calculated using the difference between the x coordinates and the difference between the y coordinates, right? So the length of AB is just cosine alpha minus cosine beta square plus sine alpha plus sine beta square, and then find its square root, right? And also A prime B prime is a square root of difference of x coordinates and then the difference of the y coordinates, which is cosine alpha plus beta minus 1 square plus sine alpha plus beta minus 0 square, right? And then find its square root. And then we can raise both of the two sides to the power of 2. In this way, we can just eliminate the radical sign in both sides, right? So we have the relationship here, and then we can just expand everything. Okay, let's do it here. So we have the relationship here, right? So if we just expand everything, we know that left side is cosine alpha square minus twice of cosine alpha plus cosine beta square, right? And then plus sine alpha square plus twice of sine alpha sine beta plus sine beta square, right? And then this equals cosine alpha plus beta square minus twice of cosine alpha plus beta plus 1, right? And then plus sine alpha plus beta square minus, no minus. Okay, and if we can just merge something, this is actually equivalent to the expression here, right? As you can see here, cosine alpha plus cosine sine alpha is 1, and then cosine beta plus sine beta is 1, and then cosine alpha plus beta square plus sine alpha plus beta square is also 1, right? So after you cancel the 1 in both sides, we can have the relationship here, which is twice of cosine alpha plus beta equals twice of cosine alpha cosine beta minus twice of sine alpha sine beta, right? And then we can divide both sides using a number 2, which is cosine alpha plus beta equals cosine alpha cosine beta minus sine alpha sine beta. Okay. Any questions? Okay, so I'll give you 2 minutes to have a look at this proof. You can also prove this this expression actually holds true for the cases where alpha or beta is 0, right? So in this way, we can prove that for any angle alpha and beta, this is actually a trigonometric identity, okay? All right, please have a look at this and do write this formula down onto your notebook, because this is the foundation for us to prove the other compound triangle formulas. All right, now let's have a look at other compound angle formulas. So basically we have already proved this, right? First one, cosine the sum of alpha and beta equals cosine alpha cosine beta minus sine alpha sine beta. We have already proved this one, right? So actually based on this formula here, we can also prove all of the following identities. So first of all, cosine the difference of alpha minus beta equals cosine alpha cosine beta plus sine alpha sine beta. And sine sum of alpha and beta equals sine alpha cosine beta plus cosine alpha sine beta. And sine the difference between alpha and beta equals sine alpha sine cosine beta minus cosine alpha sine beta. And cosine twice of alpha equals cosine alpha square minus sine alpha square equals twice of cosine alpha square minus 1 also equals 1 minus twice of sine alpha square. Okay, I'm not gonna read all of these for you. Please have a look at them. You can just write them down on your notebook first, and then in the next slides, we're gonna try to prove each of these identities. Okay, these two are also called the double angle formula. Okay, this one is also called the double angle formula. All right, please write them down onto your notebook first, and then let's spend some time to prove each of the identities here. Okay, now let's have a look at how do we prove them. First of all, cosine the difference between alpha and beta equals cosine alpha cosine beta plus sine alpha sine beta. So in order to prove this, note here we have already proved that cosine alpha plus beta equals cosine alpha cosine beta minus sine alpha sine beta, right? We can simply let the plus beta here be minus beta, right? So left side is cosine alpha plus minus beta, which is cosine alpha cosine minus beta plus sine alpha sine minus beta, which is according to this formula, which we have already proved, right? So cosine beta here is just cosine minus beta is actually cosine beta, right? And sine minus beta is minus sine beta. So this equals cosine alpha cosine beta minus sine alpha sine beta, which is actually the right side. So this property has been proved, right? Any questions? No? All right, so let's have a look at the second one. Sine alpha plus beta equals sine alpha cosine beta plus cosine alpha sine beta. So to prove this, we can start from the left side. Left side equals sine alpha plus beta. So in order to use the properties that we have already proved, we need to change this to cosine something, right? So we can use a cofunction identity. So this equals cosine half pi minus alpha plus beta, right? Because cosine half pi minus something is just simply sine something here, right? Okay, so now let's rewrite this expression inside the square to cosine half pi minus alpha, then minus beta, right? And in this way, we have cosine the difference between two angles. We have, which we have already proved that the cosine of the difference between two angles is just cosine the first angle, cosine the second angle, plus sine the first angle, sine the second angle, right? So this is actually cosine half pi minus alpha is sine alpha. This is according to the cofunction identity, right? And then multiplied by cosine beta. And then sine half pi minus alpha, this is actually cosine alpha, right? And this is also according to the co-function identity, and then times sine beta, which is actually the right side, right? So in this way, we have proved that this expression is actually also a trigonometric identity. Any questions? No? Okay, so next, because we have already proved that sine alpha plus beta is sine alpha cosine beta plus cosine alpha sine beta, right? So in order to prove this one, we can simply let beta becomes minus beta, right? So in this way, left side is sine alpha minus beta, which is actually sine alpha plus minus beta, which is according to this formula here, is sine alpha cosine minus beta plus cosine alpha sine minus beta, which is sine alpha. So cosine minus beta is cosine beta, right? And cosine alpha times sine minus beta, which is actually minus sine beta, right? So this is actually the right side. And in this way, we can prove that this expression here indeed is a trigonometric expression, a trigonometric identity, right? Okay, please have a look at this. You have any questions? No? All right, so let's have a look at the other one. Cosine 2 alpha equals cosine alpha squared minus sine alpha squared. Also equals twice of cosine alpha squared minus 1. Also equals 1 minus twice of sine alpha squared. So first of all, let's try to prove this. So cosine 2 alpha is just cosine alpha plus alpha, right? And we have already proved that the cosine of the sum of two angles is just cosine first angle, cosine second angle, minus sine first angle, sine second angle, right? And this is actually cosine alpha squared minus sine alpha squared. So the first expression has been proved is a trigonometric identity. And also note that the second term, sine alpha squared, can be rewritten as minus cosine alpha squared. So cosine alpha squared minus the difference between 1 and cosine alpha squared is actually twice of cosine alpha squared minus 1, right? And of course, the first term can be rewritten as 1 minus sine alpha squared. This is according to the Pythagorean identity, right? And then 1 minus sine alpha squared, and then minus sine alpha squared is, of course, 1 minus twice of sine alpha squared, right? So in this way, we have proved that actually this expression is a trigonometric identity. Okay, any questions? No? All right, so let's have a look at the next one. Next one states that sine twice of alpha is actually twice of sine alpha cosine alpha. Okay, so in order to prove this, so note here sine twice of alpha is actually sine alpha plus alpha, right? Because we have already proved that sine the sum of two angles is just sine the first angle and cosine the second angle plus cosine the first angle and sine the second angle, right? So sine alpha plus alpha is just sine alpha cosine alpha plus cosine alpha sine alpha. You understand? And this can be merged to twice of sine alpha cosine alpha, which is exactly the right side, right? So in this way, we have proved that this expression indeed is also a trigonometric identity. Okay, any questions? No? Okay, so now let's have a look at the compound angle formula and double angle formula for tangent x. Okay, first one, tangent alpha plus beta equals tangent alpha plus tangent beta over 1 minus the product of tangent alpha and tangent beta. Of course, alpha beta and alpha plus beta is not half pi plus k pi because these values will make the denominator be 0, right? So we need to ensure that all of the angle here is in the domain. Okay, so in order to prove this, let's start from the left side. Left side is tangent alpha plus beta, right? So according to the quotient identity, tangent A angle is actually sine this angle over cosine this angle, right? So tangent alpha plus beta equals sine alpha plus beta over cosine alpha plus beta, right? And according to the compound angle formula, sine alpha plus beta is sine alpha cosine beta plus cosine alpha sine beta, right? And cosine alpha plus beta is cosine alpha cosine beta minus sine alpha sine beta, right? And by observation here, if we want a 1 here in the left corner, we need to divide both of the numerator and denominator using cosine alpha and cosine beta, right? And in this way, the expression becomes sine alpha over cosine alpha plus sine beta over cosine beta. And then 1 minus sine alpha over cosine alpha times sine beta over cosine beta, right? And again, according to the quotient identity, sine alpha over cosine alpha is just tangent alpha. Sine beta over cosine beta is just tangent beta. And here we can also use tangent alpha and tangent beta to substitute the quotient, right? So we have landed here tangent alpha plus tangent beta over 1 minus tangent alpha tangent beta, which is exactly the right side. So this has been proved to be also a trigonometric identity. Understand? Okay, so for the next one, if we have already proved that tangent alpha plus beta is just tangent alpha plus tangent beta over 1 minus tangent alpha times tangent beta, we can simply substitute the positive beta using a negative beta, right? So let's start from the left side. Tangent alpha minus beta is actually tangent alpha plus minus beta, right? Which is, according to the formula we have already proved, tangent alpha plus tangent minus beta over 1 minus tangent alpha times tangent minus beta, right? Also note that tangent minus beta is just minus tangent beta, right? Because tangent is an odd function. So if we substitute, we can have tangent alpha minus tangent beta over 1 plus tangent alpha times tangent beta, which is exactly the right side, right? So we have proved that this expression here is also a trigonometric identity. Of course, you need to ensure that alpha, beta, and the difference between alpha and beta is not on the y-axis. Otherwise, the denominator will be 0, right? So as long as all of the angles has this constraint, this formula is a trigonometric identity. Okay, so for the next one, tangent twice of alpha equals twice of tangent alpha over 1 minus tangent alpha square. This can be simply proved by letting the alpha plus beta, we can just let the beta be alpha, right? So we can start from the left side. Left side is actually tangent alpha plus alpha. This is compound angle formula for the tangent, right? So tangent alpha plus alpha is tangent alpha plus tangent alpha over 1 minus tangent alpha times tangent alpha, right? And after simplification, we can have twice of tangent alpha over 1 minus tangent alpha square, which is exactly the right side. And in this way, we also proved that this expression here is also a trigonometric identity, right? As long as twice of alpha is not on the y-axis. Also, you need to ensure that alpha is also not on the y-axis. Otherwise, the tangent is not defined. Okay, and so in this way we have proved all the compound angle formulas and double angle formulas. And again, please have a look at them. If you haven't, write them down onto your notebook. This is a time for you to summarize and write them down onto your notebook. And for the next time, for the remaining time, we all do some practices using these formulas. Okay, so please do remember them and get familiar with them because they're very useful to solve trigonometric ratio problems in the future. Okay, I'll give you 3 minutes. All right, have you finished? Okay, so let's have a look at some practices, okay? So first example, determine an exact value for sine 1/12 of pi without technology. So I'll give you 2 minutes to think about this question, okay? All right, any thoughts? So note here, 1/12 of pi is not a special angle, right? So we cannot evaluate these trigonometric ratios directly. But note that 1/12 of pi is actually 4/12 of pi minus 3/12 of pi, right? Which is 1/3 of pi minus 1/4 pi. And we know that these two angles are special angles, right? So we can try using the compound angle formula to rewrite the expression here to sine 1/3 of pi minus 1/4 pi, which is according to the compound angle formula, sine alpha minus beta, right? This is sine alpha cosine beta, all right, minus cosine alpha sine beta, right? And sine 1/3 of pi is square root of 3 over 2 times cosine 1/4 pi is square root of 2 over 2, right? And cosine 1/3 of pi is 1 over 2 times sine 1/4 pi is square root of 2 over 2, right? So this is square root of 6 minus square root of 2 over 4, right? This is the final solution. And this is an exact value for sine 1/12 of pi. Any questions? No? All right, let's see the next example. Evaluate the exact value of the following expression without technology. Okay, I'll give you 2 minutes to think about this question. All right, have we finished? Also note here, because 1/12 of pi is not a special angle, right? So we cannot directly evaluate cosine 1/12 of pi or sine 1/12 of pi. But note here, this is actually can be rewritten as a compound angle of 1/4 pi plus 1/12 of pi, right? Because according to the compound compound angle formula, cosine alpha plus beta is cosine alpha cosine beta minus sine alpha sine beta, which is exactly what we want here, right? These two are the same. So we know that this is actually cosine 1/4 pi plus 1/12 pi, which is cosine 4/12 pi, which is cosine 1/3 pi, right? This is actually 1/2. And so in this way, we can solve this problem, right? Any questions? No? Okay, you can also check the solution in this lecture slides. All right, so next, let's have a look at another example. Evaluate the exact value of the following expression without technology. So the method is very similar to what we have seen in the previous two examples, right? Okay, I'll give you 2 minutes to think about this question. All right, have you finished? So note here, 19 pi over 12 can be rewritten as sine pi plus 7 over 12 pi, right? And according to the trigonometric identity, sine pi plus a angle equals minus sine of this angle, right? Okay, so again, this angle is not a special angle, right? But we can rewrite this angle to 3 pi over 12 plus 4 pi over 12. And then 3 pi over 12 is 1/4 pi, right? 4 pi over 12 is 1/3 pi. And using the compound angle formula, we can rewrite this to minus sine 1/4 pi cosine 1/3 pi plus cosine 1/4 pi sine 1/3 pi, right? And all of the trigonometric ratios is known to us because 1/4 pi and 1/3 pi are both special angles, right? So this is minus square root of 2 over 2 times square root of 1 over 2 plus square root of 2 over 2 times square root of 3 over 2, right? So the final result is minus square root of 2 plus square root of 6 over 4. Okay, this is the final result. All right, please have a look at this. Any questions? No? Okay, let's see. You can also check the solution in this lecture slides after the class. Okay. All right, so let's have a look at another example. Evaluate the exact value of the following expression without technology. Okay, again, I'll give you 2 minutes to think about this question. All right, have we finished? Okay, so note here this angle is not a special angle, so we cannot directly evaluate the exact value, right? But it can be rewritten as tangent (3 pi over 12 plus 4 pi over 12, right? And this is actually 1/4 pi plus 1/3 pi. And these two angles are special angles, right? And according to the compound angle formula, tangent alpha plus beta is tangent alpha plus tangent beta over 1 minus tangent alpha times tangent beta, which is tangent 1/4 pi is 1, right? And tangent 1/3 pi is square root 3, and then 1 minus 1 times square root 3, which is 1 plus square root 3 over 1 minus square root 3. And then we need to rationalize the denominator, which is 1 plus square root 3 square over 1 minus square root 3 times 1 plus square root of 3. So this minus 2 is the denominator, and 1 plus 2 square root 3 plus 3 is the numerator, which is 4 plus twice of square root 3, which is minus 2 minus square root 3. So this is the final result, right? Okay, any questions? No? Okay, now let's have a look at the third aspect of today's lesson. Okay, so far we have learned many trigonometric identities, right? There are 3 sets of identities we have learned so far. First one is the basic trigonometric identities, which can be found in the magic hexagon, right? So from this magic hex, we can find that the reciprocal identities, quotient identities, product identities, Pythagorean identities, and cofunction identities. For example, sine x is the reciprocal of cosecant x. This is the reciprocal identity, right? Quotient identity, you can start from any of the functions here. For example, sine x is the quotient between cosine x and cotangent x, right? You can start from any one of the functions and you can find the quotient identities. Product identities, that means the product of these 2 functions is the function in the middle, right? Pythagorean identities, such as if you consider these triangles here, sine x squared plus cosine x squared is 1, right? And if you consider the triangle here, tangent squared plus 1 equals secant squared, right? And if you consider this triangle here, you have 1 plus cotangent squared equals cosecant squared, right? Cofunction identity is sine x is cosine half pi minus x, something like this, right? So all of the basic trigonometric identities can be found in the magic hex. Okay, the second set of identities states that sine minus theta is minus sine theta, and cosine minus theta is cosine theta, and tangent minus theta is minus tangent theta. So note here I only list the primary trigonometric ratios. The secondary trigonometric ratios can be inferred by looking at the primary ratios here, okay? And the third set is regarding the trigonometric identities involving half pi times k. So there is a shortcut to evaluate an expression with this form, right? Suppose you have a trigonometric ratio named 1, and then you have positive or negative theta plus half pi times k, where k is an integer, right? And this is actually equals a trigonometric ratio named 2, and then theta. And then you need to determine the sign in front of the new expression. So first of all, the new name of trigonometric ratio is determined by looking at the k here, right? If k is an odd number, we need to change the name to the cofunction of the first name, right? So for example, if k is an odd number, 1, 3, 5, 7, or etc., and if you have a sign, you need to change it to cosine. And tangent needs to be changed to cotangent. And secant needs to be changed to cosecant, right? And if k is an odd number, such as 2, 4, 6, 8, or 0, or -2, something like that, the new name is the same with the original name, right? You don't need to change the trigonometric ratio name. And in order to determine the sign in front of the new expression, we assume that theta is an acute angle, and then check if this angle is in the first or second or third or fourth quadrant, right? And then use the cast rule to find the sign in that quadrant, the sign of this trigonometric ratio in that quadrant, right? And that sign is the sign in here, right? So this is the third set of trigonometric ratio identities. And today we have learned the fourth set, which is called the compound angle formulas, right? Which is listed here. So do write this down onto your notebook. This is a full set of trigonometric ratios, trigonometric identities we have learned. And based on all of these trigonometric identities, we can solve problems or applications of common trigonometric, involving common trigonometric identities, such as these four sets listed here, okay? All right, so let's see an example. Angle x and y are located in the first quadrant such that sine x is 3/5 and cosine y is 5/13. Determine an exact value for sine x plus y. Okay, I'll give you 3 minutes to think about this question. Right, have you finished? So note here we can use the compound angle formula to expand this expression, right? So sine x plus y equals sine x cosine y plus cosine x sine y, right? So we need all of the values of the four ratios here. So note here we have already had sine x and cosine y, and then we need to find cosine y and cosine x, right? Sorry, we have already had, oh, sorry. Let's write this down again. Sine x cosine y plus cosine x sine y, right? We have already had sine x and cosine y. Then we need cosine x and sine y, right? Okay, so because sine x equals 3/5, right? So this means cosine x squared equals 1 minus sine x squared. This is according to the Pythagorean identity, right? Which is 1 minus 9/25, which is 16/25, right? And because x is in the first quadrant, so note here, if cosine x squared equals this value, cosine x can be positive or negative, right? And because x is in the first quadrant, that means cosine x must be positive, right? So that means cosine x is square root of 16/25, which is 4/5, right? So in this way, we have settled the cosine x. And we can use a similar way to find sine y, because we know that cosine y is 5/13. So sine y squared equals 1 minus cosine y squared. And this is according to the Pythagorean identity, right? Which is 1 minus 25/169, which is 144/169, right? Again, if sine y squared is this number, sine y could be positive or negative, right? But note that y is also in the first quadrant. So that means sine y must also be positive, right? So according to this one, sine y here is square root of 144/169, which is 12/13, right? Okay, so in this way, we have all the ratios we need. Then sine x plus y is simply sine x, which is 3/5, times cosine y, which is 5/13, plus cosine x, which is 4/5, which we have already evaluated here, and then times sine y, which is 12/13, which we have already get here, right? So this is 15 plus 48/65, which is 63/65. And this is our final solution. All right, any questions? No? Okay, so if you don't have any questions, you can also check the solutions after the class in this slides, okay? Next, let's see another example. Prove that cosine x plus y times cosine x minus y equals cosine x squared plus cosine y squared minus 1. Okay, I'll give you 3 minutes to think about this question. All right, have you finished? Okay, let's have a look at how do we prove this. So in order to prove an identity, usually we start from the more complex side, right? So this time let's start from the left side. Left side, we can just expand it using the compound angle formula, right? So cosine x plus y is cosine x cosine y minus sine x sine y, right? And then cosine x minus y is cosine x cosine y plus sine x sine y, right? And then expand the expression, we get cosine x square cosine y square minus sine x square sine y square, right? And note that this can be further rewritten as cosine x square cosine y square minus, so note here there is no sine x in the right side, right? So we can convert the sine x to 1 minus cosine x square, right? Also, there is no sine y square on the right. So rewrite sine y squared to 1 minus cosine y square, right? Okay, and then expand again. This is 1 minus cosine y square minus cosine x square plus cosine x square cosine y square, right? Okay, so this is cosine x square cosine y square minus 1 plus cosine y square plus cosine x square minus cosine x square cosine y square. And these two terms cancels with each other, right? So this is a cosine x square plus cosine y square minus 1, which exactly the expression on the right side. So we have proved this statement here, right? Okay, any questions? No? Okay, you can also check the complete solution in this slides after the class. All right, so let's have a look at the next example. Prove that 1 minus twice of cosine x squared equals sine x cosine x times tangent x minus cotangent x. Okay, I'll give you 2 minutes to think about this question. All right, any thoughts? Okay, so this time the right side seems more complex, right? So we can start from the right side. Right side equals sine x cosine x. So note here we can convert tangent x using sine x over cosine x according to the ratio identity, right? And then minus cosine x over sine x. And then distribute this term into the square, which is sine x squared minus cosine x squared, right? And note that on the left side, there is no sine x. So we can convert sine x to 1 minus cosine x squared according to the Pythagorean identity, right? And this is 1 minus 2 cosine x squared, which is exactly the left side. So this statement has been proved. All right, any questions? No? Okay, you can also check the complete solution in this slide. All right, if you don't have any questions, let's look at the next one. Prove that sine half of x equals positive or negative square root of 1 minus cosine x over 2. Okay, I'll give you 2 minutes to think about this question. Okay, let's have a look how we can prove this. So note here, cosine x equals cosine twice of half of x, right? And according to the double angle formula, this is actually 1 minus sine half of x squared, right? And this gives us sine half of x squared equals 1 minus cosine x, right? So we have sine half of x equals positive or negative 1 minus cosine x, because we don't know which quadrant half of x is in. So we just keep the both of the positive or negative sign here, right? Okay, any questions? No? Okay, you can also check the complete solution in this slide. All right, let's have a look at another practice. Prove that sine x plus sine y equals twice of sine half of the sum of xy times cosine half of the difference between x and y. Okay, I'll give you 2 minutes to think about this question. Okay, have you finished? All right, let's try to prove this. So note here, x plus y over 2 plus x minus y over 2 is just x, right? And x plus y over 2 minus x minus y over 2 is 2y, right? So we can rewrite the left side to sine x plus y over 2 plus x minus y over 2 plus sine x plus y over 2 minus x minus y over 2, right? And then we can expand it using the compound angle formula. Sine alpha plus beta is just sine alpha cosine beta plus cosine alpha sine beta. And sine alpha minus beta is sine alpha cosine beta minus cosine alpha sine beta, right? And then we can cancel something. For example, we can cancel this term and this term, right? So this is twice of sine x plus y over 2 cosine x minus y over 2, right? And this is exactly the expression on the right side. And in this way, we have proved this statement is true. Okay. You can also check the complete proof in this lecture slides. Okay. All right. So let's have a look at the last example here. This is a real world problem that involves the trigonometric identities. So please spend some time, look at it, okay? I'll give you 2 minutes. All right, so let's have a look at the solutions. So basically there are two scenarios, right? In the first scenario, the aircraft wing is 12 feet long. And we want to determine an expression for the vertical displacement h1, right? So note here, in this right triangle here, sine x, according to the definition of sine x in the right triangle, is h1 over 12, right? And in this way, we know that h1 is actually 12 times sine x. This is the expression of h1, right? Okay, in the second scenario, we know that h2 is, so let's call this is n, and the length here is m. So h2 is m plus n, right? And m is just this length here, right? And in this right triangle, we know that m is 6 times sine x, right? And in the triangle here, this is also a right triangle, right? So n is 6 times sine 2x, right? And if we put the common factor 6 in front, this is sine x plus sine 2x. Sine 2x is actually twice of sine x cosine x, right? And then we can put sine x in front, and it becomes 1 plus twice of cosine x, which exactly the statement here, right? Okay, any questions? No? All right, so let's make a summary for today's lesson. So after today's lesson, now you should be able to understand and prove compound angle formulas. Recall that there is a list of the compound angle formulas, right? You need to remember them and do write them down onto your notebook. And use compound angle formulas to solve problems. And then apply common trigonometric identities to solve problems. Remember that we have learned 4 types of trigonometric identities, which is listed here, right? So do check all of the trigonometric identities we have learned so far. So before we leave this class, I need to mention that in the next lesson, which is Unit 2, Lesson 5, we will have our assignment 2, okay? The scope of the assignment 2 is Unit 2 L1 to Unit 2 L4. Understand? And you can use your lecture slides and homework as review materials. Okay? Please do spend some time reviewing all the materials by yourself, okay? And get prepared for assignment 2 in the next lesson.